Okay, so today we're going to go over continuous functions as we investigate its domain. Now, you may be listening to this and thinking that continuous functions, we have explored them before in previous courses, that's really easy. But it's not until we investigate how limits work within a function in order to completely understand continuity. Okay, so it's important to note a function is continuous on an interval if and only if it is continuous at every point of the interval. So basically, if you can draw the graph of the function without lifting your pencil, it's continuous, but it's over a certain interval of its domain. So if you take a look at example A, f of x equals 1 over x. So there's a way in which we can algebraically find the domain for this function. Okay, and the domain for that function, let's say A, you have to take the denominator, set it equal to 0, and solve. So this one's pretty easy. We solve, we get x equals 0. Well, that's actually where it cannot be part of the domain. So some people say there's an implied domain or a restricted domain. So that is from negative infinity to 0 exclusively, or from 0 to infinity. So this function, it is a function. It's continuous, but only on its domain, so on these intervals where it is defined. Okay. However, in B, it's pretty straightforward. We have a function. There's no denominator. There's no square root. If there was any even root, the expression has to be greater than or equal to 0. All right, we'll go back to that later. But for f of x, it's continuous for all x, so it's a constant function. A continuous function. Continuity. So constant functions, I was kind of jumping ahead, too excited here, okay, such as, let's say, f of x equals k, some sort of constant. It's continuous for all x. Polynomial functions, what we were just describing before in part B here, it's continuous for all x. So depending on the function that you're looking at, the domain could be different, but a lot of times so far we've seen that it is all real numbers. And in the next slide, you're going to see another one that starts off where it's continuous for all real numbers. Okay, so once again, absolute value functions like f of x equals the absolute value of x. This is continuous for all values of x. That is because its domain is from negative infinity to infinity. However, the next example is a rational function. Rational functions are where we see a fraction. However, there's an x in the numerator. Perhaps it's x to 0 power, but more importantly, there is an x in the denominator that is greater than 0 at an integer, usually. There's an x in the denominator with an exponent greater than 0. So if you look at this part, let me erase this. It says rational functions are continuous on the open intervals where they are defined. So we have this as an example. There are two denominators. So as I said before, set equal to 0 and solve. So if we solve these, we find out where x cannot be. So if it can't be equal to 3 and it can't be equal to 0, that's why it isn't on an open interval. That means that it's not including those values. So we have the open interval from negative infinity to 0, or the open interval from 0 to 3, or the open interval from 3 to infinity. That is where they are continuous, only on these intervals. Okay? So now it says here exponential functions logarithmic functions, and trigonometric functions are continuous at every point in their domain. So you have to know where your asymptotes are for exponential functions, log functions, particularly log functions because they're vertical asymptotes. Trig functions, you have to know your trig functions if they are continuous on all real numbers, or they're not, like let's say y equals tan of x. So that is why we have to know our common functions or our basic curves, because these are them and we need to know their domains in order to say that they're continuous on their domain for a particular interval. So, for example, I'll just give you some of the common functions, exponential functions. So if we have y equals e to the x, so this is a sketch of its graph. All right, and we can see that the domain is from -infinity to infinity. Log function. So we have a vertical asymptote if it's y equals ln of x, and that means the domain does not include 0, but it continues from there to infinity, as you're going to see. This is its graph. And just a couple of common trig functions. So, sine. It is continuous for all real numbers. And let's do, well, since we have sine there, we might as well do cosecant. And so you can see that the domain would be from -infinity to infinity, except, you know what, we're not going to use interval notation. So we're going to say all reals, except where we have vertical asymptotes, which is the equation x equals, and it turns out n pi, where n, and I'm running out of space, is any integer. Okay, so there was some additional information for you just now, and we also have this kind of summary. I believe it is in your textbook as well, but in any case, it says the function f of x equals x to the nth power for any rational n, and it is continuous on the interval where it's defined. So A we actually spoke about, but I didn't show you. A is saying that we have the equation of y equals the square root of x. You take what the expression is, set it greater than or equal to 0, and solve. Okay, so it's continuous, including 0 to infinity. From B, this is one of your common functions, and it's continuous on these two open intervals. For C, this is not a common function that is described. It is one that you can kind of sketch out. This is x to the -1/2 power. Okay, so let me draw out C. Let's try this. Okay. It ends up only being in the first quadrant. Your equation is really 1 over the square root of x. So it actually, even though we can use this expression, because it's in the denominator, it cannot equal 0. Okay, so that's why its domain is this. But we can plug in 1, and we can plug in 2 or 3, but 4 would be a little bit better because it would be 1/2, and it kind of looks like this. Okay, and so that's why it's continuous on that domain. D, we already spoke about. E, this is one of your common functions. You should know its domain. So that was a little bit background information. So just like asymptotes, the definitions involve your knowledge of limits. And that's what I said at the beginning of our lesson. So definition of continuity at a point. If it's an interior point, okay, so that's something within the intervals where we're listing. If f of x is continuous at an interior point, let's call it C of its domain, it's only because the limit of f of x equals f of c. I'm sorry, I should say that the other way. The limit of f of x as x approaches c from the left equals f of c. And the limit of f of x as x approaches c from the right equals f of c. That's the only way to actually prove that your function's continuous at a point on an interval, okay? And it has to be an interior point. We would state this. An endpoint. An endpoint's kind of funny. You can say the function's continuous at an endpoint. For example, when you have the square root of x equals y, we can say that our function is continuous and it includes 0, 0. Okay? But in order to state that or prove that, okay, we have to write that either this limit is true or that one. Okay, so let me erase this. Make sure you get this down. It's super important, and that's why I'm starring these things. So to say your function is continuous at an endpoint, okay, a left endpoint, we'll call it A, or it's continuous at a right endpoint, let's call it B of its domain. If you're proving the left endpoint, then the limit of f of x as x approaches a from the right will equal f of a. If you're proving a right endpoint, you would have to state this. The limit of f of x as x approaches b from the left equals f of b. So let's take a look at what we're saying over here. We know that if we plug in 0 for our function, so let's actually write it as a function. Then we're plugging in 0 for x, and we find that the answer is 0. Well, as you can see, that this is a left endpoint, because it's on the left-hand side. So the limit of f of x as x approaches 0 from the right, because we can only take the limit coming from the right-hand side, okay, we can see that its intended height is 0. That's what we just found to be f of a. They are equivalent. Now, you don't have to write this part, but it is important to state that since this is true, okay, f of x is continuous at x equals 0. Oops. Okay, if you find that f is not continuous, then at a point, let's call it C, we say that f is discontinuous at C, and that C is a point of discontinuity, which we'll go through in later lessons. Right now, let's focus on, we know continuous functions, and now how do we say that they're continuous at a point? And this is how we do that. Note, C does not have to be in the domain of f. And this has to do with its discontinuity. So we'll worry about that when we see it next. Okay, so here it says, it's an example in practice. It says find the points at which f is continuous and the points at which f is discontinuous. Okay, so focus on your continuity, and if it's not continuous there, then we just say that it's continuous. Okay, so this ends up being a piecewise function, and my suggestion to you is to graph it out so that we can take a look at what we're looking at. Okay, so let's stop to do that now. Okay, so I drew my axes, and really going from 0 to 4, but it's nice to see some other values if necessary. Okay, so we're going to plot from 0, so it includes this value, it'll be a closed circle, down to 1 where it's not including it, so it's an open circle. Okay, makes sense, it's a negative slope. Then we have a constant from 1. Okay, so it's a closed circle to 2, but that's not including it, so open circle. Next, we're going to plot a point, because it's only when x is 2, y is 2. And then we're going to go from 2, open circle, but that's actually already here, to when x is 3, which would be a closed circle. Let's try to make that more closed and connect that. It has a positive slope, so we're good there. And then let's go back to this color. From 3, which is an open circle, you can't really tell the difference. It's going to stay as a closed circle, to when x is 4, and it's going to be a closed circle. And that would be down here at 1. So this has a negative slope, so everything makes sense for our piecewise function. So I erased that because we did it, and let's take a look at the points where it's continuous and non-continuous. Okay, so let's investigate here. So when x is 0, where it starts, this is something we should investigate. When x is 1, when x is 2, okay, when x is even 3, and when x is 4. It just so happens to be all integer values for x, okay, but that's fine. Okay, so at x equals 0, okay, this turns out to be true. So for practice, see if you would state that it's continuous there or not. Okay, down here when x is 1. So the left-hand limit is 0, but the right-hand limit is 1. Okay, would you state that it's continuous at x equals 1 if this is true? Look through what we went over. Okay. If it's discontinuous, then write that x equals 1 is where it is discontinuous. No problem. So when x is 2, okay, the limit of f of x as x approaches 2 from the left equals 1. The limit of f of x as x approaches 2 from the right equals 1. But the limit of f of x as x approaches 2 does not equal f of 2. Okay, so the limit exists. This is true, this needs to be examined, but it doesn't equal f of 2. So is it continuous still or not? So let's look at our next one. When x is 3, okay, that's kind of in the middle. I didn't list it exactly as x equals 3. So let me try to circle that here. I was talking about the whole interval, not including 1 or 2, because we already discussed that. And this holds true. So what can we say about this interval? Is it continuous or not? Okay. Last, when x is equal to 4. The limit of f of x as x approaches 4 from the left equals f of 4. Can we say that it's continuous at x equals 4? Yes or no? If it's discontinuous, you just write x equals 4 is discontinuous. Right? We'll talk about discontinuity a little bit more in later lessons. Okay? By the way, we can't really evaluate anything for c is less than 0 or c is greater than 4 because they're not points in the domain. Okay? So we can only discuss where our function is continuous on the domain. So kind of remember that. We need to know the domain of our functions, and that's why we went over that before in our lesson. Good luck.